In this video, we're going to do a couple of extra examples working with linear functions. Okay, so let's look at this first one here. So we have a linear function. Notice it's in the form for a linear function. F of x is mx plus b, okay, where m is your slope, b is of course your y-intercept. So here's our equation. F of x is 3/5 x plus 1. Okay, so right away it asks for the slope and the x-intercept. Okay, so it's in the m times x plus b form. So that means that the slope is the m value. So it's going to be 3/5. And the y-intercept is the point 0, b. Okay, so that's going to be 0, 1. Okay, so those are our slope and y-intercept. So if we wanted to graph it, I would plot the point, the y-intercept. So I plot 0, 1. And then I'm going to go rise over run. Okay, so the 3/5 is the rise over the run. So I would go up 3 and over 5. 2, 4, over 5 to the right. Now you could also write this as -3 over -5, in which case I would go down 3 and 5 to the left. Okay, either way I get a point on my line. Okay, so this one is at 5 and 4. Okay, and then over here, I'm going to be at -5 and -2. Okay, and then if I connect those, I have my graph. Okay, so it's the graph is the line that goes through those 3 points. Okay, so that is the f of x is 3x times, or 3/5x plus 1. Now, the average rate of change, what's the average rate of change for this function? Okay, so notice they did not give me an interval. Okay, so there's no interval. Normally, when we talk about the average rate of change, there's an interval. Okay, but for linear functions, the average rate of change is constant. So it doesn't matter what interval you pick, it's always the same, and it's always the slope. Okay, so it's actually just going to be 3/5. Okay, we know that immediately. Now, is it increasing, decreasing, or constant? So our slope, m, is 3/5, which is a positive slope. So that means that as I go to the right in the x values, the y values are going up. Okay, so that's increasing. Okay, so here, f of x is always increasing and at a constant rate. Okay, so we know it's increasing. So it's increasing on its entire domain, which is -infinity to infinity. Okay, so there's one more that we're going to have a look at here, talking about supply and demand. So suppose that the quantity supplied, which we're going to call S, and the quantity demanded, which we're going to call D, of hot dogs at a baseball game, okay, are given by these linear functions. Okay, so you determine your supply using this equation here, so -2,000 plus 3,000 P, where P is the price of a hot dog. Okay, and your demand is using this equation here. So again, depending on the price of a hot dog. Okay, so it's 10,000 minus 1,000 P. So we want to solve where does S of P equals D of P. Okay, so i.e. we want to find the price P for which the supply equals the demand. Okay, that's the sweet spot. We call it the equilibrium price. Okay, so then I just set S of P equal to D of P. Okay, so that means I have negative 2,000 plus 3,000 p equal to 10,000 minus 1,000 p. Right? So if these two parts are equal, that means that the supply equals the demand. Okay, and now we just want to solve for p. So I'm going to move the 1,000 p to the left. Okay, and I'll also move the 2,000 to the right. Okay, so that gives me 4,000. P is equal to 12,000. So now if I divide both sides by 4,000, I get that P is equal to 3. So what that means is in order for supply to equal demand, they should charge $3 per hot dog. To reach the equilibrium where the supply and the demand are equal. Okay, so to find the intersection of two linear functions, you can set them equal to each other and then solve for the independent variable. So those are a few extra examples with linear functions.